Okay, today we are going to study some gambling problems, in particular the gambler's ruin problem. This is one of the oldest problems in probability theory. Okay, so let's first define what this problem is about. Suppose we have two players. One is Alice, she's the gambler, and the other is Bob. Well, this is just a name, A and B. And Bob is Alice's opponent. Okay. So they play a series of gambling bets. Okay. At each play, Alice may win. There are two possibilities. Alice either wins or loses. Okay. Alice wins 1 unit, let's say $1 from Bob, with probability P. With probability P. So this is some constant. And the other possibility is Alice loses $1, say. It can be €1, yen, or whatever. Loses $1 to Bob with probability of Q, which is 1 minus B. So these are the only possibilities. And Alice starts with, initially Alice has some amount of money. So let's say K dollars. And Bob starts with some amount of money. Let's say A minus K dollars. So together, in total, there are A dollars. Okay. And okay, so this is the second condition. And the third condition, the game ends when either player has lost his or her initial stake. When either Alice has no money, so Alice gets broke, or Bob gets broke. $0 or $0. So this is the setting of the problem. So the problem is, what is the probability that the gambler, so Alice, loses all her money or wins all the opponent's money, assuming that we can play unlimited number of plays. Okay, so this probability P and Q is the probability of winning or losing one play. Okay, and we can repeat this play until Alice loses all the money or Bob loses all his money. Okay, so we want to calculate the probability of these events. So these are the ruins, gambler's ruin problem. Next, let us formulate this gambler's ruin problem in mathematical terms. Okay. So we first introduce a random variable that it's called Rademacher random variable. Let's call it R. It's a random variable where this random variable can take two values, either positive 1 with probability p or negative 1 with probability 1 minus p. So this is much like Bernoulli variable. In the case of Bernoulli variable, it takes positive 1 or 0. But in the case of Rademacher random variable, it takes positive 1 or negative 1. But basically, it's more or less the same thing. Okay. And let's say Alice's initial stake is K dollars. Stake is K. Okay. And Bob's initial stake is A minus K. So together there are $8. Okay, K plus A minus K is A, right? So this is the total amount of dollars involved in this game. And of course, we require that A is greater than K. Otherwise, Bob's initial stake will be negative, which makes no sense. So A is greater than K. And now introduce another random variable, xn. This means Alice's stake after n plays. So for example, x1 is the amount of money Alice has after the first play, and x2 is the amount of money Alice has after 2 plays, and so on. Okay, so that means when xn is 0, then the game is over. So Alice lost all her money, and so we want to calculate this probability, for example. Okay, and x0 is of course K, because before playing any play, uh, the amount of money Alice has is her initial stake, that is assumed to be K dollars. Okay, so x0 starts from K, and eventually it may increase up to A or decrease down to 0. Okay, we want to calculate these probabilities. So in this case, Alice loses. If xn is A, then Bob loses and Alice wins. Okay. And we should note that n should be, at each play, Alice can win at most $1. So n should be greater than or equal to A minus K, which is the amount of dollars Bob has initially. Okay. And okay. Of course, if this is the case, if Alice loses, n should be greater than or equal to K, because at each play, Alice can lose at most $1. So if Alice loses, K plays in a row. K plays in a row, all losses. Then Alice loses all her money, all her K dollars. So, so this is the least amount of plays Alice has to play until she loses all her money. Okay. So our goal is to calculate this probability. Probability that xn is equal to 0 for all n greater than or equal to k. Okay? Because we know if n is less than k, then this probability cannot be positive. It should be 0 because Alice has still some money left. It's guaranteed. Okay, so this is the basic setup, mathematical setup of this problem. Okay, at this point we should try some simple example. Suppose we have uh, suppose suppose Alice has $3 to begin with. So k is 3. Then what is the uh, probability that x3 is 0? So that means, so this is initial stake. So that means Alice loses 3 plays in a row. And that probability will be 1 minus p to the power of 3, right? Because at each play, the probability that Alice loses is 1 minus p. So that continues, repeats 3 times. So that probability will be this. Okay. Of course, we're assuming that each play is independent of other plays. Okay. So that's why we can calculate this probability like this. Okay. Then what if uh, starting from $3, what is the probability that Alice loses all her money after fourth play? Is that possible? Maybe it helps to draw some graph. So initially, 1, 2, 3, Alice has $3. Okay. Suppose she loses the first play, then her money is $2. Okay. After first play, second play, if she loses again, then it will be $1. And if she loses again, that will be $0. So n will be 3 and it's not 4. So that's not the probability we want. So at this point, Alice has to win at least once. Okay, then suppose Alice loses again. Then right now she has $2. So if she loses again another play, she will have $1. So that means at fourth play, she cannot lose all her money, but she still has $1 left. However you try, this will be the case. Okay, if she wins first play, then it will be $4. And if she loses, that will be $3. Loses $2 and loses $1. And she can never reach $0 at fourth play. So this probability should be 0. And if we allow one more play, so what is this probability? So at this point, yes, it's possible. So from here, after fourth play, if Alice has $1, if she loses again, then it will be $0. So at after fifth play, the probability is not 0, but it has some value. But there are many possibilities, right? So let's see, how many possibilities are there? Okay. So that's 1. Oh. So that's 4. So 1 possibility and 2 possibilities and 3 possibilities. And how many other possibilities? So let's see, 1, 2, 3, no, maybe 3. Okay. So that means, so in any case, Alice loses 1, 2, 3, 4 times, loses 4 times, and wins one time, right? She either wins the first game or the second game or the third game. Anything else, it cannot lead to uh, this point. So 4 losses and 1 win. So that means this probability will be 1 minus p to the power of fourth times p. And there are 1, 2, 3 possibilities. So it should be something like this. Okay, in this way, we can continue calculating all the probabilities starting from x3, x4, x5, and so on. However, that is not what we want exactly. What we want is the probability of ruin itself. We don't care at what after how many plays Alice gets ruined, but we just want the probability that Alice gets ruined at some point, at any points. Okay, so that means what we need to calculate is this probability. Uh, Probability of this xk equal to 0, or xk plus 1 is equal to 0, or xk plus 2 equal to 0, or and so on. You should notice that this event, and Alice gets ruined at after kth play, or after k plus 1th play, after k plus 2, and so on. They are disjoint events, right? Because if Alice gets ruined at this point, uh, at this point, then she cannot get ruined at the next point, and so on. So all these events are all disjoint. So let's just define an event called CK that Alice is ruined starting with K dollars. Okay, so this K becomes this K. Okay, so we don't care about how many plays she has to play in order to get ruined. Okay, so that means from this discussion, we can say that the probability of this event CK is the sum of all these probabilities. Okay, so let's see. This is equal to sum of n starting from k to infinity, possibly, and all the probability of xn equal to 0. So what we really want to calculate is this probability. So how can we do that? Okay, here's the trick. First, define this event. D. Alice wins the first play. Okay, so let's see. So this is n, and we start from k dollars. So Alice, if she wins the first play, then the amount of dollars increases by 1. Okay, and this happens with probability p. And its complement means Alice loses the first play. So if that's the case, then Alice loses $1. And that happens with probability 1 minus p. Okay? Then forget about the first play and think about the probability of ruin starting from this point. From this point. Okay. So if the first play was won, then the starting point is k plus $1. Okay. So starting from k plus $1, what is the probability of ruin of Alice? And so that's one possibility. And the other possibility is that starting from k minus $1, if Alice loses the first play, then we start from k minus $1, then calculate the probability of ruin from that point. And the original probability of ruin starting from k dollars is the sum of these two probabilities, right? So we can actually apply the partition theorem. So what we want to calculate is this probability of ruin starting from k dollars, which can be split into two parts. One is the probability of ruin given that the first play was won. First play was win, and probability of win plus probability of ck given that the first play was a loss. Okay, so the complement. So this is first win, and this is first loss. Okay, so we are here using the partition theorem. Okay, and we know that this probability is p, right? It's just one play. Therefore, this probability is 1 minus p. What about these conditional probabilities? So the probability of ruin starting from k dollars given the first play was a win. Okay, so that is the probability of ruin starting from this point, right? Given the first win, what is the probability of ruin? So that will be this c probability of ck plus 1 is the probability of ruin starting from the initial stake of k plus $1. And similarly, this will be the probability of ruin starting from k minus $1. Okay, so this probability is this, and this probability is this. Therefore, okay, let's see. This is probability of ck plus 1 times p, and probability of ck minus 1 times 1 minus p. Okay. So, okay, to make notation simpler, let's define a new variable, uk, to represent probability of ruin. Okay, so this is uk, and this is uk plus 1, and this is uk minus 1. This is just a simplification of notation. And also we write 1 minus p as q. Okay, so summarizing this, we have uk is equal to uk plus 1 times p, and uk minus 1 times q. Okay, so this is a difference equation involving three terms with k and k plus 1 and k minus 1. Okay, so just rearranging this, we have uk plus 1 times p minus uk plus uk minus 1 times q equal to 0. Okay, now If we can solve this difference equation, then we know each term uk for k starting from whatever the values. Okay, and to solve this we need some boundary conditions. So that is what is u0? That is the probability of ruining starting from $0. That means Alice is already broke before even playing the first game. Okay, so this will be probability 1 because it's already Alice is already ruined for sure. And the other uh, boundary condition is this UA. So A is the total amount of dollars. So that means probability of ruin starting from $8. That means Alice has won all the dollars from Bob, right? So that means Alice has the game is over and Alice cannot be ruined anymore. So this probability should be equal to 0 because Alice is never ruined. Never ruined. Okay. So we want to solve this difference equation. Okay. It's not differential equation, it's a difference equation. With these boundary conditions. Okay, so how can we do this? That's the next problem. Now let's solve this difference equation. To solve this, assume that the solution is of this form. uk is equal to s to the power of k, where s is some constant. Okay, so we substitute this solution into here. So that will be s to the power of k plus 1 times p minus s to the power of k plus s to the power of k minus 1 times q equal to 0. And of course we're assuming that s is not equal to 0. Not equal to 0. So we can divide everything by s to the power of k minus 1. Then we have ps squared minus s plus q equal to 0. And remember, we have p plus q equal to 1. Okay, because that's the definition of q. So we can rewrite this equation as p plus q times s. Okay, therefore this can be factorized as ps minus q times s minus 1 equal to 0. Therefore, we have the values of s. That is either s equals to 1 or q over p. Okay, now let's call this value as s1 and this value as s2. Okay, so these are the two possible solutions for this difference equation. And the general solution will be of the form of linear combination of these two solutions. Okay, so let's say general solution uk is something like constant times s1 to the power of k and another constant times s2 to the power of k. Okay, but s1 is just 1, so that is just a constant after all. and this is q over p to the power of k. Okay, now we have to determine these constants based on the boundary conditions here. Okay, so if we put k equal to 0, use 0, so k equal to 0, that is a1 plus a2, which is equal to 1. And ua is a1 plus a2 s2 to the power of a, which is equal to 0. Okay, from these simultaneous linear equations, we can determine the values of a1 and a2. Let's first determine the value of a2, and let's see. Subtract this one, the second equation from the first equation, then we have a2 1 minus s2 to the power of a equal to 1. So from this we have a2 equal to 1 over 1 minus s2 to the power of a. But in order to divide by this, we have to assume that s2 to the power of a is not equal to 1. Okay, otherwise we cannot determine the value of a2. Okay, so this is the case where s2 to the power of a is not equal to 1. That means s2 is not equal to 1, and that means q over p is not equal to 1. So that means p is not equal to q. Okay? If this is the case, oh, if this oh, if this is the case, p is not equal to q, we can determine the value of a2 like this. Okay, so for the moment, let's assume this is the case. Okay, so if that's the case, then we can now determine the value of a1 from this first equation. That is 1 minus a2, which is 1 minus 1 minus 1 s2 to the power of a. That is, let's see, s2 to the power of a over 1 minus s2 to the power of a. Okay, so substitute these values of a1 and a2 back into the general solution. We have uk equal to s2a over s2a plus let's see, s to power of k minus over 1 minus s to power of k. Wait a minute, something is wrong. Let's see what's wrong. Okay, so this should be negative sign here. Yeah. Okay, so this is s2 to the power of k, s2 to the power of a, 1 minus s2 to the power of a. So this is the general solution of this difference equation when p is not equal to q. Okay, so this means P is okay. So since we have where is it? This relation P plus Q is equal to 1. P equal to Q means they are both equal to 1 half. So this P not equal to Q means P is not equal to 1 half. Okay. So what if then P is indeed equal to 1 half? When P is equal to 1 half, which is also equal to Q, then what? Okay, so how can we solve the case for P equal to 1 half? In this case, if we go back to the previous process, here, look at this. So first we assume this form. Then we got this solution for S. But when P is equal to 1 half, then the two solutions of this quadratic equation is both 1. So we have S equal to 1, and that's it. And nothing else. It's a repeated root of the quadratic form. So as another solution, another possible solution, we assume, suppose uk is equal to k times this repeated solution, 1. That is just k. Okay. So let's see what happens. In this particular case, we have 1 half k plus 1 minus k plus 1 half uk minus 1 equal to 0. So if we assume this form, does this satisfy this equation? Let's see. So that is 1 half k plus 1 minus k plus 1 half k minus 1. So we have okay, let's see, 1 half k plus 1 half minus k, 1 half k minus 1 half. So this will cancel, and this will be k, which is cancelled by minus k. So this is indeed 0. So that means this particular solution, this special solution, satisfies this equation. So now we know that so we have now two special solutions. That is 1 to the power of k, 1 to the power of k, and k. Okay, so the general solution is a linear combination of these two special solutions. Okay, so this is a1 times a to the power of k, but that is just 1, so I just omit it. And to determine the values of these coefficients, we use the boundary conditions again. So u0 is a1 plus a2 times 0, which is a1, is equal to 1. So it's easy. A1 is 1, and UA is A1 plus A2 times A is equal to 0. And we know A1 is 1, so A2 is minus 1 over A. So after all, we have UK equal to 1 minus K over A, or A minus K over A. Okay. So this is when P is equal to Q, which is equal to 1 half. So to summarize, we have the general solution of this difference equation. given the boundary conditions. As this, uk is equal to, what was it? S to the power of a minus, no, it's power of s to the power of k minus s to the power of a over 1 minus s to the power of a. I think this is right. Yes, so this one. If p is not equal to q, or a minus k over a if p is equal to q, which is equal to 1/2. So this is the general solution of this equation. And of course this s is q over p. And now that we know the probability of ruin of Alice, it is easy to calculate the similar probability of ruin for Bob. To do so, we just switch the roles of P and Q. So replace P with Q and replace K with A minus K for Bob's ruin. So suppose, let's see, V A minus K is the probability of ruin of Bob, with initial stake of A minus K dollars. Okay, then just switching these variables in the solution of Alice's probability of ruin, we can prove that, you should try that yourself, and this probability should be 1 over s to the power of a minus k minus 1 over s to the power of a over 1 minus 1 over s to the power of a, and that is when p is not equal to q. Or it is k over a when p is equal to q is equal to 1/2. Okay, and in either case, this or this, we can see that uk plus v a minus k is equal to 1, right? Let's see. By the way, this s is the same as before, that this s is equal to q over p, right? Okay, so what does this mean? uk is the probability of Alice's ruin starting from k dollars, and va minus k is the probability of Bob's ruin starting from a minus k dollars. So together, so the game ends either in Alice's ruin or Bob's ruin. So the game can stop in either way. So that happens with certainty. That is probability of 1. So that's what this means. So this game ends certainly, almost certainly. Now consider a different problem. Well, actually, it is still a problem of gambler's ruin, but we now look at the duration of the game. So that means how many times do we have to play until the game ends. That is until Alice or Bob becomes broke. Okay, so of course this duration is a random variable in the sense that the number of games we have to play depends on time to time, right? In one time it may end in three times, three plays, and the game is over. Sometimes it may take 100 plays until the game is over. So the number of steps to termination is a random variable. The number of steps to termination. This is a random variable. It's a random variable. And also let's consider the initial capital. Initial stake is also a random variable. Stake of Alice. And what we are interested in is this probability. That is, given the initial stake of K dollars, what is the probability that the game terminates by n steps, at n steps? Okay, so this is a, this is a conditional probability that the game terminates at after nth play, given that the initial stake of Alice is K dollars. Okay, so this is the probability, and what we want to calculate is this expectation value. Expectation value of n, given that the initial stake of Alice is K dollars. And the definition of this expectation value, conditional expectation value, is this: sum over n from 0 to infinity and n times the probability, conditional probability. Okay, let's call it D. Okay. Okay. So now we want to derive how to calculate this quantity. Okay, before deriving the equation for dk, first we note that Pn given k satisfies this equation. And given k, if we sum this probability from 0 to n equal to 0 to infinity, it adds up to 1. Because this is because the game ends eventually, right? So at some point the game will end. So this is why this holds. Okay, now just like we did before for deriving the probability of ruin, consider this diagram. So this is the number of steps until the game terminates, and this is the initial stake Alice has, and we start from K dollars, and in the first play Alice either wins or loses. So if she wins, her stake increases to K plus $1. If she loses, her stake becomes K minus $1. And suppose, starting from here, the game ends at nth play. Okay, so somehow after Alice either wins or loses the first play, the game will be over one way or the other at nth play, suppose. Okay, So either Alice wins all of the dollars or she loses all of the dollars. Anyway, so uh, this conditional probability P given n given k can be split into two parts, depending on the result of the first play, either win or loses. And in either case, after winning or loses the first play, there are n minus 1 plays left. Okay. So after winning, so suppose, then at least the game will be terminated within n minus 1 plays, given k plus $1. Or Alice loses the first play and the game ends within the next n minus 1 plays, given k minus $1. Okay. So this is another application of the partition theorem. Okay, so if we apply this equation to the definition of dk, which was the expectation value of the number of plays until termination given k dollars as the initial stake, the definition was this: n from 0 to infinity n times Pn given k. So for this part, we substitute this. Okay, so that will be, just substitute from 0 to infinity and n p times Pn minus 1 given k plus 1 and q Pn minus 1 given k minus 1. And we expand this and factoring these constants out, and we have p and n and q and Pn minus 1 k minus 1. Now if n is 0, then this n is 0, so this whole factor will disappear. So we can just start from 1. But this part is n minus 1 and this part is n. So let's see. We substitute this n minus 1 to, let's say, m. Okay, so n will be n plus 1. Okay, so substitute this to here and here, and substitute this to here and here. Then we have p m from 0 to infinity and m plus 1 pm k plus 1, and m from 0 to infinity m plus 1 pm k minus 1. Okay, so again, expand this, distribute this term, m plus 1 p minus 1, and so we have p in sum of m times pm given k plus 1 And look, this part is m from 0 to infinity and just p, m given k plus 1. And for the second summation, for this summation, we have similarly q times m from 0 to infinity m p m given k minus 1 and q from 0 to infinity p m given k minus 1. However, as we have noted before, this part and this part are both equal to 1. Okay, so this part is equal to 1 and this summation is equal to 1. So we just replace with 1, so we have p plus q here. Okay, but p plus q is 1, so together this is equal to 1. After all, and also, let's see, this part is dk plus 1, right? And this summation is dk minus 1. So after all, we have p times dk plus 1 plus q times dk minus 1 and plus 1. And that is the difference equation determining dk. And now we are going to solve this difference equation. So how can we solve this equation? First of all, let's rearrange this. P dk plus 1 minus dk plus q dk minus 1 equal to negative 1. So it's just rearranging. Okay, and we also need the boundary conditions, right? So in this case, the boundary conditions are this. Starting from $0, the game ends at immediately, so that is 0. And starting from $8, the game also ends immediately. So these two conditions are the boundary conditions. And this equation, this difference equation, looks quite similar to the one we have encountered for calculating the probability of ruin. But there is a difference. That is this part. Previously it was 0 here, but now we have a constant, non-zero constant. Therefore, this is a kind of inhomogeneous. Difference equation. Previously it was 0, so it was called homogeneous difference equation. It's just like differential equations, homogeneous differential equations or inhomogeneous differential equations. So as a general rule of thumb for solving this kind of difference equations, first we need to find the solution for homogeneous case. That is, pretend this constant is 0, then solve it. And actually that is already solved before, right? We already know the answer. And that is something like this. A1, A2, S to the power of K, where S is Q over P, right? If P is not Q. First we consider this case, okay? Then, by whatever means, we find a particular solution of this equation, okay? Then, the sum of the particular solution and this general solution will general solution for the homogeneous equation will give us the solution for the inhomogeneous equation. So that's the general strategy of finding the solution. So what would be the, so we already know the general solution for the homogeneous case. So what is the particular solution for this inhomogeneous equation? So let's try of something like this: dk equal to constant times k. Does this equation satisfy, does this solution, tentative solution, satisfy this equation? Let's try. So let's substitute this p times c k plus 1, because this is k plus 1, minus ck plus q c times k minus 1, because this is k minus 1. And is this equal to negative 1? Let's check. So this is PCK, PCK, and PC minus CK, QCK minus QC. And let's see. Have this and this. So P plus Q, CK minus CK. And let's see. And PC minus, let's see. Let's see. PQC. And P plus Q is 1. So this is 1. So this will cancel this. So after all, we have P minus Q times C. If this is equal to negative 1, then C, the constant C, must be equal to negative 1 over P minus Q. Now that we have this constant, so the particular solution is this. Let's change this to Q minus 1 over Q minus P. So the particular solution can be written as K over Q minus P. And the general solution is the sum of this particular solution and the general solution. So the general solution is a particular solution. The general solution will be K over Q minus P plus A1 plus A2 times S to the power of K. Now, A1 and A2 are some constants which are to be determined from these boundary conditions. So let's see what we can get. Okay, so D0, if you put 0 here, it's 0. And this is A1 plus A2. That should be 0. And dA, if we put this, that is A over Q minus P, A1 plus A2 to the power of s to the power of a. So from this we have a2 is minus a1, and this is equal to 0. So qp a1 minus a1. So let's see. That is a1 minus sa is equal to minus a over qp. So a1 is minus a qp 1 minus s to the power of a. Okay, so that's it. The general solution is k over q minus p minus a qp1 minus sa and plus a qp a times s to the power of k. So yeah, this should be the final solution. Maybe we can make it a little bit prettier. Let's see, how can we do it? We factor this out, and minus a1 minus s to the power of k over 1 minus s to the power of a. Yeah, so this is the general solution when p is not equal to q. Now, as you can see, if they are equal, this will be a problem. But since we're assuming this, it's okay. So, similarly, if p is equal to q, in this case it's actually equal to 1/2, then we can apply the similar approach. That is, first solve for homogeneous case, then find some particular solution, which may be a little bit difficult, but not too hard to guess. Then after all, we should have this solution. You should try to derive this. Okay, so this is the solution when p is equal to q.